Hello friends, today we see Johnson's method. Here are the steps of Johnson's method by normal specification. First step, we select the independent geometrical parameters. Then we decide what is the objective of our optimum design. Means under what objective we generally do the optimum designs like weight, cost, strength. Suppose we want to design for weight, so for minimum weight we want to design our component. In this way we finalize our objective, and according to that we can specify geometrical parameters, means diameter, length. Then we next step is to write down the primary design equation, which is the main equation of the design. Primary design equation, it is always depends on what is the objective we finalize. According to that our primary design equation should be. Next step is we write the subsidiary design equation. When you design the component, we know that there are multiple equations we are using. So subsidiary design equations are maybe one or maybe more than one. Then we write down the limiting equation. Limiting equation generally equation of stress, factor of safety, or maybe in numerical some value range is given of some component. Suppose the length is should not be more than 1 meter. It is come under limiting equations. Next step is we classify the parameters. Generally when we write down the parameters, we know that we select the geometrical parameters, we take the material parameters, and we try to fulfill our functional requirements. So generally three categories of parameters in the design: functional requirement parameter, material parameter, and geometrical parameters. In the functional requirement parameters, again we can say desirable effect parameters, undesirable effect parameters. When we see the numerical, we can see all this. Next step is to combine subsidiary equation with PDE, because we want only one equation to simplify. So we have multiple equations, primary design equation, subsidiary design equation, limiting equation. Now we try to combine this. So first we combine subsidiary equation with primary design equation by eliminating the common parameters. Next step, we impose limiting equation on primary design equation. We again combine these two equation. Then we write final primary design equation in terms of parameters group. Means geometrical parameters we try to separate, material parameters we try to separate according to our requirement. Then in the numerical, different materials are given, so we put one by one material parameters in that, and we find out the geometrical parameters, and from this we decide which material it is optimum for our design. Then next case, we find out the size of the parameters, means we have to find out the geometrical parameters, and in this way we do the optimum design by Johnson's method. Here we see the example, one example of helical compression spring. In this the force is given 1000 Newton, stiffness is given 70 Newton per mm, factor of safety for shear it is given 1.5, spring index is given 5, wall stress factor it is 1.3, and we have to design for minimum cost. So the objective is minimizing the material cost, and we neglect here the inactive coils, and one table is given for different material M1, M2, M3 and M4. Four materials are given there and their properties are given. Now first step, again we write the primary design equation, and it is always related with the cost, as our objective is cost. So we write down the equation in terms of cost. C is the parameter of cost, Cm it is cost of material, small c is the parameters related with the cost, into volume into density. Volume into density means as the material cost is depends on weight, kg, it is per kg. So we write the equation into C into W, that is W means volume into density. So volume we know it is A into L. A it is pi by 4 d square, and L we know for the spring it is pi dn, where d is the coil diameter, n is the number of active coils, small d is the wire diameter. Then we try to simplify this as the spring index is given, so we eliminate one parameter, it is capital D by small d, and as whatever the parameters given in the numerical, try to input all these parameters in the equation. So in this way we write down the primary design equation. Next step, we have to write down the subsidiary design equations which is related with this. So first equation, as we see in the numerical, stiffness is given, we write down the equation of stiffness, but stiffness equation, it is we directly not put in the primary design equation. To combine this equation afterwards, we write this equation in terms of number of coils, because n is there in the primary design equation. Then we write subsidiary design equation, that is second equation. Again it is shear stress equation, as yield strength for shear is given, factor of safety is given. So write down the shear stress equation. Again we modify this equation in terms of d by c, small d by c, that is d square by c basically. And we see in the primary design equation, d square and c is there, so we can easily replace and put the value of this equation afterwards. So we modify this SD2 in this way. Next equation, it is limiting equation, and we know that limiting equation, it is generally with the stress, but it is also related with factor of safety. So we write down the limiting equation. Tau max is nothing but SYT by FOS. FOS factor of safety, SYT we know it is the yield strength, tau max it is a shear stress. Now we classify the parameters. How we classify? See here in the table, functional required parameters and which are specified. So we write in the specified column, functional requirement parameters are whatever the force required, whatever the factor of safety which is expected, which is specified. Then stiffness. Undesirable effect parameters, you see here in the limited column, that is a tau max. Always shear stress or maybe any stress value we keep for any component at a minimum level, so it is a limited and it is an undesirable effect also. Cost, see we don't know, it is not a specified, so it is come under unspecified and unlimited column. And again we require to, this is the effect, again it should be minimum, so it is come under undesirable effect parameters. Next is geometrical parameters. Geometrical parameters value we don't know, so we write unspecified or unlimited, that is small d, c and n. Material parameters generally small c. Cost parameters, that is related with material. Then rho, SYT, G, all these are the material parameters that is related with the material. So first we combine two equation, that is primary design equation with subsidiary equation 1, and subsidiary equation we write in terms of small n, that is number of active coils. So we put that equation and we replace n here. See here is n, in the next equation n is replaced by that equation of K, stiffness equation. Now this modified equation we combine with SD2. SD2 equation, it is of stress, so we replace again d square by c. See here it is d raised to 4 by c square is here, capital C square. So we replace this by our tau max equation, which we write SD2. So in this way we get the modified equation, again that is modified primary design equation. But again we have to combine one more equation, that is limiting equation, and in limiting equation we replace tau max by SYT by FOS, and then we get this developed PD. This is a modified equation. Again we make the groups of the equations. Here whatever the value specified in the numerical, we make a separate group of fixed values, and we make one group of material parameters, because for the every material C value is different, small c, that is a cost value per kg, rho value is different, G value is different, SYT is different. Here we see the material selection parameters or material selection factors, and you see same table which is given in the numerical I put here, and when I make one more column, it is related with material selection factor. So here we observe M1 material have a less value of material selection factor, and other value in the developed PD it is fixed value. So whatever the value of material selection factor, it will decide which material is optimum, and from this table it is clearly observed that M1 material has a less value of material selection factor, so that is the optimum material. And for this, from the table we can easily estimate the value of CM value, and from the SD1, SD2 we can easily calculate the value of small d, that is wire diameter, and again capital D, mean coil diameter, and number of active coils. In this way we can design the spring, helical compression spring, for minimum cost. Now instead of cost, suppose in the design it is mentioned to design for a minimum weight, then our primary design equation, it is related with the weight. Then we know that weight is nothing but mass into m into g. See here, primary design equation, it is related with the weight, and we know that the weight equation m into g. So from this we can again write down volume density into g. We know that we have to calculate the volume into L. A, it is pi d square. We know that the length is pi d, and d is the mean coil diameter, N is the number of active coils. So in this way our primary design equation, it is changing. So here we see the subsidiary equation SD1, SD2, it is not going to change, as whatever the values given in the numerical, they are fixed values. Again we design the same component, only our objective is changing. Again the limiting equation is same, classification is same. Again when we combine the equation, again the combinations are almost same, only change. So here we combine the SD1 equation with PD equation, primary design equation, we get the modified primary design equation. In the second case, again we combine SD2 with PD equation. Again we get one more equation, modified equation, by eliminating the common parameters. In the next step we again combine limiting equation of stress, we replace stress equation by SYT by FOS, and from this we get a developed PD. Again when we make the group of the parameters, see here, again we make the whatever the fixed value of parameter in the numerical, that is in the separate group, and material parameters in the separate group. So for fixed parameters, whatever the parameters specified in the numerical which have a fixed value, we get one value for this. And again material selection factor, it is only rho g into SYT, our small c, which is in the cost parameter, or it is neglected here. So here we see material selection factor rho g by SYT square. As we design only for weight, so material cost factor parameter or factor, it is not there, so it is only rho g by SYT square. And in C, in the column, last column, material selection factor column, again when you calculate the value for all these four material, now according to weight, M3 get less value, so we can select M3 material, third material, for our optimum design, because according to the weight our answer is different, and according to the cost, whatever the answer initially we get, that is different. So when our objective is changing, automatically whatever the answer it is changing, so you get a different value of CW according to weight, and we also get the different value of diameters, coil diameter or maybe the wire diameter, and number of active coils. Again follow the same procedure as we do in the initial case. To calculate these parameters, we are using again SD1 SD2 equation to find out the parameters or maybe the dimension of this spring. Thank you.